In this video, we'll be solving problem number 64, minimum path sum. So the problem states that we are given with a m cross n grid which is filled with non-negative numbers, and we have to find a path from top left to bottom right which minimizes the sum of all numbers along that path. And we can go either down or right at any point in time. So if we are standing at any cell, we have two options. So for the first example given, this is the path which gives the minimum sum, which is 7. In the second example, it is 12. So we can take deeper look into these examples and understand the problem. So this is the first example. If we are anywhere in the grid at RC, we have two options. We can either go to the right and the index will be R and C plus 1, or we can go down to R plus 1 and C. Similarly, we can see in the grid also at places we have two options, which is shown by black marker. And another thing to note is that at the last column we only have one option because there is no right. So if we are at the last column, we can only go down. And similarly, if we are at the last row, we cannot further go down. We only have option to go to the right. So with this example, we can follow 1, 3, then 1, then again 1, then again this one, and it will give the minimum path of 7. If we take any other path, the resultant will be more than 7. This was the second example. In this also, we can take 1, 2, 3 and 6, which will give 12 as our answer. So this was 12. We see that at any cell we have maximum two options. So this can be drawn as a decision tree. So if we are at 0, 0, we can go either to 1, 0 or 0, 1. Similarly, this tree can be built with all the options, and eventually we will reach the bottom right of the grid, which is 2, 2 in our case because we have taken 3 cross 3 matrix. So to solve this problem, we see that from 0, 0, we can ask two adjacent cells, 1, 0 and 0, 1, what is the minimum path from U to reach the bottom right. Similarly, this guy will ask its again neighbors 1, 1, 0, 2, what is the minimum path from U to reach the bottom right. Similarly, this thing continues. So we can build a recursive solution to have these two decisions and take minimum between the two. So every time we have two choices, it will again ask two choices. So between the two, we will take the minimum and the current value of the grid to add to the solution. So we'll start writing the code here. So we'll take rows and columns separately so that we don't have to call this again and again. And we'll also take a cache. So here we see that there are several nodes which are repeated again and again. Like here we see 2, 1 repeated here, and then again here, then 1, 2. Similarly, there can be several nodes that are repeated. This is a small tree wherein we have lesser number of nodes. For a bigger tree, there would be many more nodes which are repeated, and we don't want to compute for the repeated nodes again and again. That's why we'll take a cache and save the result to it. And after this, we'll create our function min path, and it will take row and column. So this is the starting point. From this R and C, what is the cost to reach the bottom right? It will return that value. And we'll have some base conditions. If we are at the destination where we want to reach, then we can return the value of the grid, this last thing. And if we are at the last row, then we only have one option. Actually, we can check for cache also. If RC cache, then we already know the result. And if we are at the last row, we can update the cache. This should be grid current value plus min path from now we are at the last row, so we can only change the column. We can only go to the right. Another condition is if we are at the last column, then we can again update cache and RC and min path. Now we can only change the row. We can come down because we cannot go further right. And last condition is that we have both the options. We can go down also or right also. So in this case, see, this will be equal to grid of RC plus, now it will have min of both the, either we should go to right or down. So it will be minimum of both. R plus 1 and C, and in the end we'll return cache. And in the main function we'll call this function, but with 0 and 0 index, because we have to start from 0 0 index. So this function actually returns the sum of path. If we are at RC, what is the minimum path from RC to reach the bottom right? So this function is essentially returning this, and this is the tree as we saw. So from 0 0 we'll call two functions, from 1 0 again we'll call two functions, and ultimately minimum path will be accumulated and returned. So if we open the console and run this code, yeah, accepted. Now I'll submit. Got accepted. So in this solution, the time complexity will be m into n. M into n is the number of elements in that grid, and space complexity will also be m into n, because we are taking cache and we are keeping RC to it, so this will also be m into n. So this was the first approach to solve this problem, and this is a dynamic programming problem, and this type of approach is called top-down approach, or recursion plus memoization approach. Now we'll see the second approach, which is the bottom-up approach of dynamic programming. So in this approach, what we'll do is we'll think in the reverse order. So ultimately we want to find from 0 0 we have to reach 2 2. If we take 3 cross 3 matrix, the first example, then this will ask its adjacent neighbors. 2 2 can be reached from 1 2 or 2 1. So it will ask, so cell 2 2 will ask 1 2, what is the minimum path to 0 0 to 1 2, and similarly it will ask what is the minimum path from 0 0 to 2 1, and path from 0 0 to 2 2 will be min of these two, because these two are adjacent and 2 2 can be reached from either 1 2 or 2 1. So minimum of these two plus the value of grid 2 2 will give the minimum from 0 0 to 2 2. Similarly, this continues as in the last approach, but we are thinking in the reverse order. So this can also be coded, but instead of recursion, we'll take a iterative approach and we'll update the grid in place to avoid the space that we took in last. So I'll reset this. Again, we has to take and calls equal to len of grid of 0, and then we'll loop on all the rows. So we see that if we are on the first row, the only possible choice to reach 3 is via this cell. So that's why we are updating these two things, first uh, the first row and the first column. Here we are updating the first column, which is this one. Similarly for, and column is variable here. So with this thing, what we are doing is, for the first column, we can reach here from this cell only. We can reach here from this cell only. That's what is being updated by this first loop. And by the second loop, what we are doing is, we are on the first row itself, because this is always 0, and we are looping over the column. So on 3 we can reach from this one only, and here we can reach from this one only. So this kind of becomes our base case for us. Now we'll run on the matrix. R and C will be min of grid R minus 1 C, or grid R or C minus 1. So min of these two will give the result for the current grid position, and in the end will return grid of rows minus 1 and calls minus 1. So we can see this again to understand this. So ultimately we have reached from 0 0 to 2 2. So that's what the first question that was asked, and this will ask its neighbor cells. 2 2 can be reached from 1 2 or 2 1. So here we see 2 2 can be, or in fact we have added indexes here. So 2 2 can be reached from either this one or this one. So that's why this cell asks what is the minimum cost to reach u from 0 0, or what is the minimum cost to reach to u from 0 0, and it again asks its neighbor cell. So this way it continues. And for the first row and first column, there is only one way to reach, so that's why we have updated that. So we'll run this. We'll submit this. Yeah, this is also accepted. So its time complexity remains same, because we ultimately has to look at all the cells in the grid, so it remains m into n, but the space complexity reduces to order of 1, because we are not taking any additional memory. We are instead updating the grid in place. So the input itself is being updated, so we are not taking any additional space. So in some cases where we cannot update the input, we'll have to take some other approach. We can either make a copy of grid, or some other way. So to summarize, in this video we saw two solutions for this problem. First one was the memoization and recursion approach, which took order mn, time and space complexity. And then we saw bottom-up approach, which took order of mn, time and constant space. So that's it for this video. See you in the next one.